Hello, welcome. How are you tonight? Welcome back, everyone, for Unit 5 seminar. How are you? Some interesting changes happening this unit. We're going to be talking about algorithms and looking at a coding exercise in our homework. I'm going to tell you more about that in a minute. If you like coding, that's something that you can look forward to this week. If you're not sure or on the fence about it, then it's a good kind of onboarding, a good kind of trial run of what coding entails. Yeah, it's also different in our discussion this week. Absolutely. Glad to hear that some of you are taking a, you know, early look at those instructions for discussion. That's always a great idea, just to give yourself a heads up what the discussion work is going to entail for the week. Any questions from anyone before we get started on our content for Unit 5 tonight? Anything that you're wondering about? Anything at all? Everybody feeling okay? Know that we are just about halfway through the course, so it is a good time to kind of take stock of where you are and just ask if you are okay. If that is the case, then great. Just keep on maintaining and persevering on that pace if you're happy with how things have been going. If not, that's okay, because we still have a lot of time left in the course. And so now is a good time to take a good look at your grade book, ask yourself what's been going well, ask yourself what you might want to change if you think you need to change in any way, how much time you spend on, say, discussion or how you approach preparing for a quiz, whatever it may be. Think about those kind of things as we are approaching the middle of the course so that you set yourself up for success in the latter half of our time together. Sorry to hear that, Andrew. I know some others expressed that in email earlier this evening. I hope that everything's going okay, at least without power. I know how that is, being in hurricane territory. I've been there. Found last week challenging, Alan. So that's a good thing. A little bit of a pinch or challenge is useful for our learning intent. Go ahead with that question, Eva. We're going to be taking a look at um, that lab exercise, and I'll show you some tips on that. But if you have any specific questions for right now, feel free to ask. Great, Michael. I'm glad that you tried that out and that you found it helpful. I've had kind of a mostly positive response from students who try out the tutors, and so that's why I make that one of my strongest recommendations. Um, if you don't have the best experience with a tutor in your first time trying them, try someone else. Take a look at some of the schedules of other tutors and try a different one, because sometimes it's just like a personality match, right? Not everyone is destined to work with everyone else. So, Michael, thank you for sharing that. And I'm using that as a plug to try out the Math Center tutors because they can be very helpful. I don't have any control over our quizzes, Serena. Sorry about that. Whitespace does not allow me any authority to open up quizzes early or to shut them down or to create some other schedule that they're not currently on. I wish I could. So with that in mind, plan around as best possible. To go in on Friday. You can always look ahead to the Unit 6 Zybook's homework. That's always open. Chapter 6 is already open. So one strategy might be to work ahead this week if possible, and then get your quiz in on Wednesday or Thursday. That's just an idea. I know that's kind of a short timeline, but just your mentioning what you're, what you have on the horizon. Just wanted to brainstorm a little bit there with you, see if we might come up with some ideas on how to approach. Great, Michael, glad to hear that. And Michael Peck, try them out. Anybody unsure of how to find our Math Central tutors? If that's not possible, I have, and others in our department have verified that all of the questions have real solutions. So if you have a specific question about one, and you want me to clarify later, you can always take a screenshot of the question and email it to me. So go back through those quiz results and take a screenshot of it and send it to me. I don't think I've received an email from you about that, Eva. Oh, I see. Yes, okay. I do see those questions. I had to remind myself real quick what those questions were that you sent. Yes, those both had solutions. So I'll be happy to talk about those in the last few minutes of seminar as we have time. I'll be happy to offer my thoughts on those two questions that you sent me. Let me see what question number that was. Not 17. But if you have a question about number 17, Alan, I'd be glad to take a look at that with you. All right, so we need to get started here on our Unit 5 content. And just, about the experience that you had with the tutor that's why I say if you didn't have a successful meeting with them in that time, maybe try one of the other tutors in the Math Center in a second meeting or a second try of using the tutor services, because they are human too, right? And so they might look at a problem and feel like they're in the same boat as you some of the time, because the expectation is that they would not be expert in everything. They are very well equipped and very knowledgeable about how to do various problems in math, but they may not have the answer to every single thing you might present to them. So if after meeting with a tutor, if I've encouraged you to meet with a tutor, and then afterward you still have a question about that exercise, you and the tutor spoke about it and they were not able to help you resolve it, then come back to me and let me go over it with you. I'll be happy to do so. All right, just wanted to clarify, the tutor experience is not just go to the tutor and then if it works, then that's the end. Feel free to continue the dialogue, bring it back to me, and let's all work together in that loop to make sure that you get closure in that question loop. All right. Okay, Ella. Was that question number 4 or 14, just so I know for later? Okay, great. Awesome, Michael. All right, great feedback about your experience with the tutors, and I welcome that at all times. Let me now just turn the video off so that we can see the slides a little bit larger and we can start talking about what we have going on in Unit 5. So we're looking at sequences and series as well as algorithms. You get a little bit of a break from quizzes this week, so that's a nice thing. And we're going to have a little bit of an extra kind of activity in the homework that is a programming lab. So that is kind of under the big umbrella of algorithms or things that are a step-by-step protocol, and often that term is used to express something that is done by computing, a step-by-step algorithm by computer code, in other words. So I just said it. An algorithm is a step-by-step, unambiguous procedure for solving a problem. And some terms that we might throw around in relation to algorithms are variables are names given to a receptacle that's going to store a value. And to trace means to simulate the steps of an algorithm and attempt to generate what would be the output or the answer. So let's try this one out. We have input A, B, and C, and we're comparing them to see what is the smallest of these three numbers. So if we're going to trace this algorithm for A equal 8, B 5, and C 9, then let's look through the algorithm and see what's happening. We're going to set our variable to small. Michael, that can be part of an algorithm. Yeah. Let me know if you want further verification. We're going to trace our value, which is stored in the variable small throughout this algorithm. So at first, it is assigned the value 8 by that line, small equal A. And then we make this comparison if B is less than small. So is that true? B less than what's in small right now? Yes. So we're going to execute the then component of that statement. So we're going to reassign small to the value of B, which is 5. And then we'll move on through the algorithm. We're now going to make the comparison of C to what is stored in the variable small. So is 9 less than 5? And the answer is no there. So we will not execute the statement coming after then. And just for the sake of representation, the variable small still has the value 5 in it. And we're going to now output the result of that variable is 5. Fairly simple example here, but you get the idea. It's a step-by-step process by which we achieve some goal, and here we're looking for what is the smallest in a list of numbers, basically. If you wanted a mnemonic trick or memory device, you could say the pointed end is smaller than the open end. So you're asking yourself, is the number to which the pointed end is facing, is that smaller than the number to which the open end is facing? We're ending with the value stored in the variable small, Chandy. I wouldn't characterize it as the program or algorithm ends at B. So we ended with scrolling over all of those input values and updating our receptacle that's storing the smallest element as we went through all of those comparisons. I get where you're coming from, but to characterize this algorithm as just shutting down at B, regardless of what the inputs are, doesn't fully take into account what this algorithm could do, right? Because these numbers could be different. A could be 1, B could be 11, and C could be 1/2. And then we would be executing and changing the value of small when we get to C. So depending on the outputs, this algorithm will operate or kind of it will change in the way that it unfolds throughout the trace. Great suggestions there on how to think about the less than operator. And then recursive algorithms are those where they invoke themselves. In other words, an algorithm that within the body of it causes it to start over with some other input value, usually. Here we have an example of that. If we start a algorithm with the value in the first receptacle A1 equal to 4, and then every subsequent receptacle AN is computed from the previous one plus 2, then we can code that or process it with an algorithm that is recursive. Sequence N is a recursive algorithm where N is the number of elements to be in the output array. And here we're going to say that if N equal 1, then AN equal 4, else invoke the algorithm for N minus 1 plus 2, and output the array AN. So if we call for sequence 5, in this case, then what we would be doing is for our array AN, we are working through sequence 5. So when N is 5, this part does not execute. This part does, and so we call sequence 5 minus 1 plus 2. So the first step of this algorithm calls sequence 4 plus 2, and then sequence 4 is going to generate sequence 3 plus 2, and so forth, and we wind up with the sequence by this recursive process, invoking the algorithm several times over, and then it kind of backs out of itself, you can imagine, and produces all of that intended output, with the sequence here being 4, 6, 8, 10, 12. And while we are here, let me turn our attention over to our live binder for this week, where you're going to find some additional helpful information. Some of you may already be in the habit of looking at our live binders, but it's critical for this week, I would say. So link over to your live binder for Unit 5, and let's see what you can use here. First off, that example that we were just looking at, that is right here. I explain it in even more precise detail how you can think about that recursive algorithm playing out. So I'd encourage you to take a look at that video if you'd like some additional insight into that recursive algorithm. Also in the homework this week for chapter 5, section 8, you have a lab that involves programming in Python to generate the results of various summations. And I provide a video here that walks you through how to think about approaching that lab, what some of the symbols mean, what some of the language means when it says compute the summation sum ij equal, and it has numbers in brackets. The way that it's spelled out there in typeface, I recognize is not clearly intuitive. So that's why I provide this video in which I write out, as you can see there, when we read that line that says sum of whatever, and how do we interpret that? That caret 17 doesn't necessarily mean the 17th power, and what they've spelled out there, it means that's the value that we're taking that summation to. And so watch that video to understand how to interpret each of those blocks, what the intent is, and also how you might approach the coding aspect to make it efficient. Reuse code as needed, copy paste and edit and so forth. Also, if you're not familiar with Python syntax, there is a walkthrough here where you can find all of the symbols involved with Python coding. I'm opening that up now so we can just take a quick look at that. Michael, that coding component, section 8, is a piece of the homework. Yep. I'm not quite going into that realm of technicality, Eric, but I'm glad you mentioned that. I'm glad you're aware of that. I meant more in the sense of you're maybe not typing every single letter out. Because when you get to block 2 and block 3 and block 4, you should be able to reuse a lot of what you've already coded, right? Rather than just typing from scratch lines over again. So that's kind of what I meant. And I'm impressed that you took my mention of efficiency and recalled that in mathematical terms, that means what is the order of your algorithm? Absolutely. All right. So as you see here, this is a nice little roadmap of what are some symbols that are commonly used in Python. You'll see the exponent operator, notice, is not what we would intuitively think of because a lot of other calculators use the caret symbol for exponent, right? But notice this handy reference tells us that that's the double asterisk. We want to take an exponent, double asterisks. Also in this document, you have some notes on every single block. If you want to look at this in more detail, I would suggest a combination of looking at that video and having this handy for reference as well. And then you have other, excuse me, a little bit of a throat cold this week. So I'm kind of trying to get on the other end of that. You have some other examples about, you know, the models that we're talking about this week, like sequences, and sigma notation. So remember that LiveBinder just generally can be a useful resource for video content related to the topics of the week. But for this homework in particular, I strongly encourage you to use these 2 tabs for section 5.8, and that will set you up to be successful next week in our Unit 6 lab where we code as well. We're going to have one in Unit 6 as well. So think of this as a 2-unit experience in how to think through algorithms and code them up in practice. All right, let me get this back in here. For the quiz, I don't think so, Michael. That's a great question. You might just be asked kind of like a general question about, what does the trace of this algorithm excuse me, produce as output? What does the trace of this algorithm produce as output? I think that's the extent to which you're going to see questions related to algorithms and coding on the quiz. You're not going to be asked to code actively on the quiz. All right, let's take a quick break here. I'm going to drink some water and get situated for our second half. We'll come back at 10:30. If you have any questions right now that you would like addressed, please let me know. And Eva, on that question 14, you had everything set up in what you sent me. What you need to do, like if a blue die shows number greater than 3, that's 1/2. Red die shows number less than 3, that's 1/3. So probability of A given B is the intersection of those two. 1/2 times 1/3 is the top piece. We need the intersection on the top. And those two die are independent. One's blue, one's red. So they're not affecting one another as far as their outcomes. And then item B there was the red die shows a number less than 3. So that was the 1 or 2. So that's 2 of the 6 outcomes. That was the 1/3 piece. On the denominator, that's where we put probability of B. Probability of A given B is their intersection over the given. So that comes after the given bar here. So once we have all of those items in place, we can reduce, and this is 1/2, or 0.5. And some of you have emailed me about the redundant zeros. Whenever Brightspace, our quiz environment, asks you to do something to a certain number of decimal places, just go ahead and throw them in there. That way you'll be given the credit right away. If you forget, or if you notice after that something was glitchy like that, or not sort of the norm, then feel free to email me and I'll be able to correct that. Something like if you entered 0.5 rather than the zeros, as it says to do all 4 decimal places. Did that help, Eva? I'm sorry that the tutor wasn't quite clear on how to approach that question. It's kind of tricky because you have 2 things that are totally not influencing one another, right? So it may feel odd to be saying, okay, what is the probability that something happens on the red die given something happens on the blue die. And this is something that comes out of conditional probability, is that when things are independent, you might as well just look at the probability of that thing happening on the independent event. Notice this thing worked out to simply P of A. And that's a property of conditional probabilities. You don't have to know that. You can just execute the conditional probability formula and get to the correct answer like we showed here. But that's kind of the takeaway. We have two things that are independent of one another, and yeah, what's the probability of this thing happening on one of them, given that this other thing happened on the other event? Well, if they're not influencing one another, that basically breaks down to just the probability of what, how much that happens on the first thing, or event A. I see, Eva. Yeah, sometimes we get kind of tangled up in the complexity of things, especially like conditional probability, because it is one of the more challenging things related to probability. So I would say, don't beat yourself up over a problem that involves conditional probability, because that is one of the more challenging aspects of probability. Good effort, but don't hold yourself to that standard of perfection like we often like to, right? I know, because I'm in that group, and we want to do well and want to get things right. It doesn't always work out in our favor, and I've had those experiences myself, even with math classes. When I was in graduate school, there were some areas of mathematics that I absolutely detested. I would like to have thrown my book off of a rooftop. I was just, at that level of not understanding it, or not wanting to understand it even at a certain point. We shouldn't get to that point, or it's hard not to get to that point sometimes. So take your, let's see, what's the best way I could frame this advice given my experience and my sort of hitting the ceiling of mathematics I felt. Don't take it personally. It's not that you need to master everything. The important part is just giving it your best effort, trying to make incremental gains in your understanding, taking what you can from the experience and journey, and using it in your future. And who knows, maybe somewhere down the road, you'll have an opportunity to revisit something that you didn't quite understand on your first pass, and then be able to take it with you with understanding on that second or third experience of seeing it somewhere down the road. That's been my experience as well with statistics. I hear you, Eva. Past probability. Probability is actually one of the hardest areas of mathematical study for the population at large. So if that's any consolation, you can take that with you. Thank you for sharing that experience, Tyler. That's good to know. Use a different calculator if the one that you are using doesn't give you something that's not in scientific notation. And that's a great attitude, Joshua. I commend you for that, taking that stance. Yes, absolutely. Try to break the mold. And that's okay, Yavor. You don't have to, make perfection on all of them. I encourage you to kind of think about your coursework in terms of averages. If you averaged 90% or better across your unit assignments, then you're clearly in like A minus A territory, right? So if you got 100 on your homework, and you got 100 on your discussion, and you got 100 on your seminar, and then you got an 80 on your quiz, perhaps that averages out to 91 or 92 or something, right? So that's where I'm coming from. Kind of think about piecing together all the pieces of the puzzle that is our grade book, and think in terms of averages. That way you can kind of give yourself a little bit of wiggle room for learning and not too much self-deprecating thinking, or, I didn't get the best score on that quiz. Oh, woe is me. Try to avoid that. All right. Moving right along to sequences, series, and summation notation. Sequences are a series of numbers, or sequence of numbers, I should say. Here are some examples like perfect squares, 1 square, 2 square, 3 square. Fibonacci sequence is one that is recursively defined, right? We name the first two elements, and then the subsequent ones are the sum of the previous two in that Fibonacci sequence. The perfect square sequence can be defined as n squared, with n being the index of the sequence. Prime numbers is just kind of like an off example, or one that is based on definition. We can't write a formula for that particular sequence. I just wanted to give you kind of a broad overview of what are some examples of sequences here. A sequence is a set of objects called elements or terms that has a particular order, and a sequence is composed of a set of natural numbers arranged in a particular order mathematically. One that is finite has a countable number of elements. Terms or elements are particular numbers within the sequence. And when we look at that notation A of n, or A sub n, that's stating a general term for any nth index within the sequence. The first term, the second term, whatever we use in the number for n. General term is also a phrase that we use to mean the formula for terms of a sequence. So when we label a term AN, you can think of just straightforward starting elements of a sequence, like A1 would represent the first term, A2 the second term, A3 the third term, and so forth. Let's take a look at these. If we define the sequence A of n equals 3n minus 2, that's going to look like, let's just kind of make ourselves a note board here. For n equal 1, 2, 3, and 4. What do we have? For this particular sequence, when we plug in 1, we get 3 times 1 minus 2 is 1. 3 times 2 minus 2 is 4. 3 times 3 minus 2 is 7. 4 times 3 minus 2 is 10. So we're just plugging those in values into the formula to get first 4 terms of the sequence. The second one, when we plug in 1 for the power on -1, that determines the sign. So with the first one, we got -1 to 1. power. So that produces a negative 1 on the top, divided by 1 is negative 1. Second term, negative 1 squared is going to be like negative 1 times negative 1, or positive 1 over n is 2 here. So you get the pattern, the alternating negative signs over the index. Negative 1, 1/2, negative 1/3, 1/4. So some key takeaways I want you to notice here. Look at the structure of that sequence A. There's a common difference of 3, right? And then if we think about the underlying basic sequence of 3s, 3, 6, 9, 12, then we have the amount that we need to add or subtract, -2, right? Visualize that basic sequence from your common difference. Basic sequence of 3s is 3, 6, 9, 12. That's 3n right there. How do I get to 1, 4, 7, and 10 from that? -2. So that's how you can build the formula, by looking at the numbers, because you will be expected to go in both directions. I know we were given the formulas here, and we wrote down the first 4 numbers, but you also want to start thinking about, how do I get back to the formula, or how do I write the formula if I were given the numbers? And so notice in that first sequence, we have difference of 3 between every term. That tells us our multiplier on the index, 3 times n. And then we can think about what the basic 3 times n sequence would look like. That's the 3, 6, 9, 12. Compare that to the sequence we're looking at, and that tells us the plus or minus part, -2 in this case. What I want you to take away from example B is that to get alternating signs in a sequence, we need a -1 to some power. It can be either n, or it can be n plus 1 if we want those signs to be in the alternate places. We would make the power n plus 1. We wanted to shift the sign. So those are some key notes that you want to keep in mind for building sequences. Take a look at another example here. 5 times n plus 2, that's 7, 12, 17, 22. So go back and practice your formula building mindset. What's the difference here? Right, it's 5 on every term. So that tells us the first building block of our formula, 5 times n. Then we imagine the 5n sequence. You can see how to get to the original sequence from there, plus 2. Here's another one. Notice we're not given the formula this time, we're just given the first 4 terms of the sequence. So use those strategies that we've been talking about. Give me your best estimate for what the formula of this sequence would be. You're right in identifying that common difference. What do we do with that 1? And then where do we go from there? Just as a reminder, that common difference is what we multiply by the index. So 1 times n. And then we can visualize the 1 times n sequence. And then add 2. So our formula here is n plus 2. Always check your sequences as well. After you've written the formula, check your first couple of terms. Plug it in equal 1 in there. Make sure you get the first term. Ever notice if you did that on your n plus 1 guess, then you'd see you start from 2, then 3, then 4. So that's why it can be useful to check yourself on the first couple of terms after you kind of have your initial estimate of what the formula may be. You don't necessarily have to write it down perfectly from scratch. A little bit of trial and error is actually encouraged. I know I'm writing these down kind of straight off from scratch, but you can approach these in a little bit more of a trial and error manner. What do we have going on here? What do you notice that's particularly something we should take note of here? Alternating signs, absolutely. That's what I would want you to take note of first. So you need a -1 to some power. We don't know what that power is yet. Let's just try n. Okay. And then we have some 5s. And that's going to be to some power 2, right? Because these are now multiples of 5, not just adding 5 between each term. So our number this time is going to have n on the power instead of times n. 5 times n would be like 5, 10, 15, 20. 5 to the n power is how we get multiplying 5 across each term. So what do I get if I use this formula? What are my first couple of terms? I plug in a 1, I get -1. If I plug in a 1 on the 5, I get 5, so I get -5, right? If I plug in a 2, I get positive from the -1 squared, and then I get 5 squared is 25 for positive 25. So almost there, but by trial and error, we see we need to update our formula somewhere. What do we need? What needs to change? -5 is not the answer. You had to give an explanation of how this does not match what we're trying to get. What would your explanation be? Changing up a bunch of what we've already tried is not what you want to do. You want to stick to what you've started with. So that's a good first step, Michael. Something needs to happen with the negatives. What can we say about what's going on with the negative signs here? Switch them to different place throughout our sequence. And so you're saying switch. Imagine the next one. That would be -125. So it's more about displace or move ahead or change the position of, not just switching those two, but it's moving the negative over in your sequence, moving it to the next term, making the 5 positive, making that 25 negative, making that negative 125 positive. And remember, the way that I suggested doing that was to change your power on the negative 1. So change your power here to n+1. We're not going to edit anything here because our numbers themselves are working. We're going to keep 5 to the n as is. And now when we plug in n equal 1, we get a 2 on the power of -1. So that's going to make it positive. And we plug in a 1 here, and we get a 5 out. And we plug in a 2, we've got an odd number on the -1, so it's going to be negative. Plug in a 2 on the 5 and get 25. And get an even power when we plug in n equals 3, so we get a positive here, 125. So on this particular example, we have the general term, or the formula is -1 to the n+1 and 5 to the n. All right. Michael, I think so. I'm not quite sure what you mean by if the numbers are matching, consider the power. If the signs are matching what you have in your original sequence, then you don't need to edit it on the -1. If the signs are not matching, then you need to shift them over 1. And you can do so by placing a +1 on the power that's associated with the -1. That's kind of how I would wrap up this entire example. Also, an important thing to note is that you don't want to mix your -1 with your multiplier. You want to keep them separate because in this case, notice that -1 has a different power than the 5 in order to have the output that we need. And that's exactly what it is. A lot of the time, Michael, when you're trying to come up with the formula for a sequence, it doesn't always need to be that you write it down perfectly first try. In fact, I would actually encourage a little bit of trial and error because you can learn a lot in the little tiny mistakes that you correct throughout a trial and error approach. Absolutely. This is the same rundown. And notice you can even shift that power by doing -1 if you wanted to. I would just stick to +1. So before we end tonight, we need to take a quick minute or two to talk about series. Series is taking a sequence and writing all of the terms as a sum, and then maybe even calculating that sum, maybe just expressing it in summation notation. So here's just kind of a general outline of what we mean by a series, taking all the terms from a sequence and adding them together. If you have a countable number of terms, then that series is finite. If it's not countable, then it's infinite. For example, in this particular series, this is summation notation using this symbol called sigma with your starting index given down here, starting at k equals 3, and your ending index up here, 6. We're going to execute k squared for this. So we start from 3 squared plus 4 squared plus 5 squared plus 6 squared. So that is 86. K is our indexing unit. The sigma, which looks like an E, the Greek letter sigma, that stands for take the sum from k equals 3 to 6 of k squared. So let's take a look at this one. We have take the sum from k equal 1 to 5 of k over k squared plus 1. So we could write out all of the terms of that, as you see here. Be careful when you have k in several places. It can be easy to kind of forget that. Like I've caught myself at times, maybe just writing 1 here, instead of remembering that that's actually k up there too. So just kind of watch yourself if you've got the variable in multiple places. We're not going to find common denominators and add these up, but you see the expression of the summation given in those 5 terms. Imagine we want to go the other way around. That works a lot like what we were just doing, trying to write down the formula for a sequence. We first need to do that, write down the formula for the sequence, and then we would write down the summation part. What is our summation part here? From k equal 1 to what? 6. We've got 6 terms. What is that going to look like? We've got a -1 to the n plus 1 over something involving k down here, right? 2 times k. That might entail a little bit of trial and error on your part. Maybe you start with just n on your -1 and then recognize that that produces negative sign first, then positive sign second. Oh, so then I need to add 1 to the power on my -1 in order to get the right signs in the right place. And then I need to think about how do I produce that 2, 4, 6, 8, 10, 12 in the denominator, and that's by 2 times your index. And then there is a lot more detail that we can go into related to sequences and series known as arithmetic and geometric sequences. What the classification into arithmetic or geometric allows us to do is to use their respective formulas as a kind of more efficient means of coming up with what is the formula for the sequence, or coming up with what is the sum of this series. And so arithmetic sequences are those where we said, okay, the differences between all of these terms was blank. Like this right here in the denominator is arithmetic, common difference of 2, right? That's arithmetic, common difference of 2. Go back here. This, geometric, common ratio, which is the multiplier of -5 in this geometric sequence here. So if you're multiplying to get to each sequential term, that's geometric. If you're just adding to get to each subsequent term, then that is arithmetic, like adding 2, adding 2, adding 2. So that's the fundamental difference between arithmetic and geometric sequences. What they allow you to do is start from their kind of textbook formulas if you want. rather than that trial and error process, you could, if you identify the sequence as being arithmetic, you could use this formula to come up with its formula for any specific arithmetic sequence. And likewise, you could do so for geometric, like you see here. There is also some very useful summation strategies for arithmetic sequences. Like if you wanted to find the sum from 1 to 100 of some arithmetic sequence, like n plus 2, then you could use one of these two formulas to find that sum of the arithmetic sequence. And you're going to have some practice with these greater details in your guidebook homework this week. So like I've said in the past, I believe if you want to follow along with more slide examples, download them from Virtual Office and you can flip through more slides if you like to see those examples. And then whenever you're ready, even if that's right now, if you don't want to look through the rest of the slides, that's fine. You can just go directly to your guidebook lab homework and start practicing these concepts there. Let me know if you need anything throughout the week, and next week you will have a guest professor. So that's something to look forward to. I'll see you again myself in Unit 7. Professor Bernhardt will be joining you all for Unit 6. She's an excellent professor on our staff, and she's looking forward to being with you for the Unit 6 seminar while I have to be away. Have a great week, everyone. I will be available by email all throughout the next couple of weeks, so don't be shy to reach out to me. Anything you have, anytime, let me know. Have a great week, and I look forward to seeing what you have to share in this week's discussion. And I hope that you have fun with our programming lab in section 5.8 of this week's homework. It's a really good skill and a great way to practice on a pretty light set of exercises. Remember those live binder help tools for that lab 5.8. Good night, everyone. Sounds good, Ella. I'm glad we were able to clarify that question on conditionals for you too. No worries, Michael. Excuse me. All right, good to hear. Glad you're nice and cool now. Got all but 2 already, Eva, that's excellent. Maybe give it a break and come back to it. Yeah, take a look at the live binder maybe. Good night, everyone. Great to be with you tonight, and I wish you the best in the next week. Let me know if you need anything anytime.